Hyperloop, and our job in whole is to manufacture a fast-moving pod that can transport humans at lightning speeds. So I'm sure if you're all familiar with Elon Musk's white paper of Hyperloop, which is a vehicle, a transportation vehicle, which solves modern day problems of moving fast. So we here at Hyperloop are building a scaled-down version of this, and we want our Hyperloop pod to go at 50 miles per hour with 50 feet of track. So our design team will go over the constraints and design qualifications they made to ensure that our pod, as you can see right here, can meet those requirements and travel at our expected rate and brake safely.
Yeah, so for overview of manufacturing, last semester I was the lead for the manufacturing team, and I helped the Hyperloop team by basically providing the parts and creating the parts for first prototype of the team. And we did a lot of the design work for the I-beams, as it was more cost effective to 3D print the I-beam parts rather than machining them. And this semester my main focus was on incorporating some of the mechanical design analysis into the making of the Hyperloop pod. So I ran workshops on how to conduct flow simulations on SolidWorks, stress analysis on SolidWorks, and by helping the team, and you'll later see in the slides, we were able to do a thorough analysis on our pod and make it more aerodynamically efficient and pinpoint some of the stress concentrations on our model.
So as a consultant member, I was tasked to create pod drawings of specific parts. These pictures are drawings of the I-beam track and the base layer drawing. So this semester I've learned how to do isometric drawing with geometric dimensioning and tolerancing. So I was able to measure each of the parts, their length and the widths, and also in doing so I learned how to create 3D solid parts into drawings using this program called SolidWorks. And with that, I also learned how to do detailed sections, detailed views of certain parts of the drawing so you can see a better view. And then also, I also learned how to do section views of the parts, as you can see in the base layer. It's important to have these drawings neat and readable, because if you're giving these drawings to somebody else, you want them to be able to read and understand what's going on, and also reproduce that part, whether it may be plastic or metal.
So over the semester, I was in charge of making the brake system. So here, our brake system is composed of a clamping mechanism, as you can see over there. This braking system is going to be reducing speed from the theoretical max speed of 50 miles an hour to 0 within 10 feet. Because it's a floating caliper design, it's going to be able to respond pretty quickly to braking. And it's also integrated into the pod frame. So not only will it help brake, but it's also an important member of the structure of the pod. Over here you can see our calculations to calculate exactly how much force we need. So to our left we have our calculation using our conservation of momentum to figure out that we need about 288 newtons of force for friction to stop the pod. Over here we calculate the normal force. And so the braking system was divided into two parts because there's two systems, one on each side. So each system needs to provide about 288 newtons of normal force to stop the pod. And so here are the components. We have the high torque DC motor, our brake pads, our power screw, and we also have a gearbox to help amplify the torque. So over here we have our equation to figure out how much torque we need from the motor to actuate the power screw to convert the rotational motion of the motor into the linear motion that will stop the pod. And here we can use our linear velocity equation to figure out exactly how long it will take to actuate our brake mechanism, which is around 0.39 seconds. So here are our theoretical motor speed. According to the website, was around 0.00357 newton-meter torque, and our motor speed was at 6,000 RPM. This is at half stall torque and half maximum RPM at no load speed, because that's for maximum power delivered. But we gave it a 90% of the maximum power when we did our calculations to account for any frictional losses or any inefficiencies in manufacturing the motor. So our target performance is around 0.128 newton of torque at the screw, and the speed of the screw should be on 1080 RPM. So we use our gear ratio equations to figure out that our driven gear must be 90 teeth and our driver gear must be 18 teeth to keep the motor at its power band. Alright, so this is our braking system. As you can see, our floating caliper designed with the power screw over here to make that linear motion occur, as well as a rod helps guide the brakes so they don't like twist or anything. Alright, so this is our assembly. So as you can see over there, the brake system is integrated into the pod on the top and on the bottom to help with structure. And so in order to test our brake system, we're going to use a force sense resistor to figure out exactly at what actual torque does the motor stall at, as well as how much normal force does it actually produce. And an important aspect of our design is to make sure that our pod is able to stop even if the main power is cut. So we're going to use the linear velocity of the pod and then convert that back into power into the brake motors. So the motors of the driven motors of the pod will create the energy required to stop the pod.
The purpose of the Hyperloop pod cover is to protect interior electronics from any outside element while also making the pod more aerodynamic. My initial prompt was that the pod cover cannot interfere with the electronics part of the pod, represented by the 4-inch red box. These were some initial iterations that I came up with at first, and they're just variations of general aerodynamic shapes. In my second week of creating the pod cover, I determined that the pod cover should slant all the way down to the track in order to encase the entire top portion, and I created these 3 new iterations. Since iteration 3 was the shape we were looking for, I moved on to the design phase. To attach the covers to the pod body, I used 8 832 1-inch hex screws taken directly from McMaster car. There are 4 to hold the top and 4 to hold the bottom. I created new threaded holes on top of the pod body so it would match the screws, and they are labeled by the red arrows. On the covers themselves, I made new columns inside which correspond with the threaded holes on the pod body. And lastly, this is a section cut view of the entire pod assembly, which shows how the covers are attached to the pod body. First, the top cover is attached from the bottom of the pod, and then the bottom cover is attached from the outside holes. It can only be assembled in this order because the bottom cover closes up the interior, prohibiting access from the top portion and the electronics portion of the pod assembly. To disassemble it, we would just detach the covers in the opposite order.
After finalizing the design, the next step was to take this design and run a flow simulation on it in SolidWorks, with our main goal being to find the coefficient of drag on this shape. So we ran our flow simulation at our theoretical target speed of 50 miles per hour, and we see that the air is speeding up towards middle cross-section of the design and slowing down towards the back. Figure 20b shows the contour line plot of the velocity, and it's behaving as expected since it's symmetrical design on both the left and right, instead of having one side elongated. And the symmetrical design is due to the pod traveling in both directions without it either rotating on the track or spinning, since we want the same coefficient drag on both sides. And finally, to find the coefficient drag, it was solved in 2 ways. The first was in SolidWorks using the global equation goal, with the drag force being the total force in the x direction, and the average value on that chart was verified by hand using the drag force equations and the greatest cross-sectional area of the pod.
So after all the designing and simulations, we finally landed on a design that we all like. But turns out when we looked up how to manufacture it outside, it costed $10,000. So at first we thought we hit a roadblock. We can't make this. We don't have this kind of funding. But thanks to our president here, who has this workspace at home, and I can point out there's 5 printers here, 5 on the other side, and because of this, we were able to print this out. And our printer being used here is a CR30 belt printer with infinite Z length. The material is PLA, and outsourcing cost is $10,000, but printing it in-house is only $100, and that's including electricity and also all the material, which is 765 grams of PLA. And to fit the size constraints of the printer, we have to cut it in half. So we have 4 pieces, 2 on top, 2 on the bottom, and here you can see this is one of the bottom covers. That fits like right here. So in these pictures from left to right, you can see the printing process for the Z clamp, base layer, and bottom cover.
Alright, thank you guys. Do you have any questions? Yes.
How does the pod handle like a curve?
Currently, we are assuming that the track is straight because in particular to the competition we're entering, the track is a straight track all the way for 1 mile. However, that's a really good question because our pod cannot handle curves. Yes. In order to handle curves, we need to put springs on the wheels so that it will attract itself to the track. And if it encounters like a bend or a curve, then these springs will compress onto the track and allow us for some leeway to make that turn. Yes.
How do you float the brake?
Yeah.
What's it attached to?
So it's attached to a power screw, yeah, so it's a screw mechanism, and then that itself is attached to both the frame of the top and bottom, as you can see. So this right here is it'll attach the top part to this frame, and then the bottom frame down there, and it'll keep everything centered towards the screw.
For the failsafe, you mentioned that you would use the linear motion of the actual pod itself to regenerate power. Now, are you assuming that it's a failure from an outside electrical source or within itself?
So one of our fail-safes is, or one of our failures that can happen to the pod is if like suddenly it loses all the electricity in it, right? And that can happen because of a loose wire or because something hit the pod. And in that case, we want the pod to break immediately.
Okay.
So in order to detect this, we will be using the excess current generated by the inductance of the motors to feed back into the brakes themselves. So once it detects that current spike, we have a circuit that will allow the pod to realize that the power has been lost and immediately break the pod down.
Any additional questions from the audiences? If no question, let's thank them for their excellent presentation.